This video draws together the previous videos in this chapter and makes a recommendation for horizon choices. Just some reflections then, or reminders of things that we've already said. The optimization of J is only meaningful if the optimized trajectories are close to the closed-loop responses that result. So if the optimized trajectories differ from the closed-loop responses, it suggests you'll keep changing your mind, and therefore the optimization doesn't make sense. Also, if the optimized predictions differ significantly from the closed-loop behavior, then the predictions you're using are meaningless, and the optimization is meaningless, as they did not represent what is actually going to happen. So those 2 points are really saying the same thing. But also, we want a close match between the predictions and the behavior that we actually want, the closed-loop behavior that we want. There's a difference between the closed-loop behavior you get and the closed-loop behavior that you want. And here the focus is on what do you actually want. And if the optimization cannot deliver what we want, then the optimization isn't really doing what we need it to. So some examples in the early videos have shown that if there's a close match between predictions and closed-loop behavior, and this will happen if and only if some conditions are met, and we're going to elaborate slightly on those conditions to come up with a proposal for how you might choose your horizons. Now, the numerous examples we've used tended to indicate that the output horizon should be well beyond the system open loop settling time, so that any tracking errors that are ignored are essentially zero. The input horizon must be long enough to capture, and here's the key point, the entire desired closed loop input trajectory, because otherwise there's a mismatch between what you want and what the optimization can deliver. And if there's a mismatch, the optimization is not going to be able to give you what you want. The required horizons may change with the control weighting, as the weighting has an impact on the desired speed of response. So what that means is the horizons aren't dependent on the example or the process, they also depend on things like the control weighting. How do we choose these parameters then? Now, the key thing is, we've just said, what constitutes a long enough prediction horizon and a large enough control horizon is not fixed. But typically, the output horizon should be a little over the open loop settling time, but you might want it to be longer if the target closed loop dynamic is slower than the open loop dynamic. The required input horizon depends upon the open loop behavior. If the open loop behavior is good, then you might find that nu equals 1 is all that you need, because all you want is one change in the input to get it to the steady state. If the open loop behavior is bad, you need to know how many control moves are required while, and this is the key thing, not overactuating, so in terms of what magnitude of input increments are you allowed, and you need to get to the steady state, you need to manage the behavior in transients and in steady state and so on. So the key thing is here, how many control moves do you need in order to achieve all of those things? And it might not be clear-cut. And that's the key point. It may require some trial and error simulation to establish the horizons that you actually need. So you might not be able to say what they are up front. So here's a simple proposal for how you can find the horizons that you need. And I'm going to emphasize this is for open loop stable systems only, and it assumes that you've got no problem with computer accuracy or numerical ill conditioning and the like. The first step then. Choose an NY and an NU which are obviously much larger than you require. Then design your predictive control law and find the closed loop responses. Now obviously this is all at the moment by simulation, so this is setting things up. So choose a very large NY, a very large NU, do the closed loop responses. Once you've done that, identify the length of the key input and output dynamics and select these as the appropriate minimum choices for the NY and the NU that you actually need. So here's an example. Example 1, same example as we've used in the previous videos. You'll see what I've done is I've chosen a very large NY and a very large NU, ridiculously large really, 40 and 20, and said, okay, what closed loop responses do I get? Now in this particular case, you can see that the output has pretty much stopped moving by around here, and the input has pretty much stopped moving by around here. So what I can say is that an NY greater than something like 8 is going to capture everything that I need, and an NU greater than or equal to 5 is probably going to capture everything I need from the input. So what I'm going to do now is choose NY equal to 10 and NU equal to 5 and see what happens. And there we go, and you can see I've overlaid in this plot the responses with NY equals 10 and NU equals 5 with the responses I got up here with a very large NY and an NU, and you cannot see any difference. So NY10 and NU4 give near identical control to NY40 and NU10, and what that tells you is that NY10 NU5 is going to be big enough to give you what you need. Here's a different example. It's the same underlying system, but I've now increased lambda, which slows down the response a lot. So again, I've chosen NY40, NU20 as my first step. I'm identifying the key dynamics. You can see the output settles around there by about 16 samples. The input settles by around there, which is somewhere around 7-8 samples. So I'm going to choose NY15 and NU7. And let's see what we get. And again, what do you notice? That if I choose NY15, NU7, I get the same closed loop responses as with NY40 and NU20. And in fact, you get away with using smaller values if you really want to. Not that I would necessarily recommend that you should, but you can. Example 2 then. This is the example with a non-minimum phase characteristic. And here, again, you see I've started my test with NY equals 40 and NU equals 20. And what I found is the output dynamic pretty much stops changing somewhere around there, which is after about 10 samples, and the input dynamic pretty much stops changing somewhere around there, which is about 5 samples. So if I use NY equals 10 and NU equals 5, then I should get a controller which does what I need. And lo and behold, what do you notice? With 10 and 5, I get near identical control to NY equals 40 and NU equals 20. Third example. Again, you see I've got NY equals 40, NU equals 20 to capture the key dynamics, and you can see again the output's pretty much stopped moving around there. The input has stopped moving somewhere around there. So in this particular case, I've chosen an NY of 8 and an NU of 6. And what do you notice once more? That with 8 and 6 you get nearly identical control to NY equals 40 and NU equals 20, so 8 and 6 will probably be enough. And example 4, this is the one with the significantly oscillatory dynamics. So here I've chosen a very small lambda, NY equals 40, NU equals 20, and what you notice is the output has settled very, very quickly, and the input has settled moderately quickly. So I have chosen an NY of 6 and an NU of 4. I've done my closed loop responses, and what do you notice? That you've got nearly identical control. You could try a smaller NU, and you will see that if you take a smaller NU than this 4, you no longer get this overlap. The performance starts to degrade. So some reflections. Long enough cannot always easily be defined in advance. The output horizon must be some samples, but it might only need to be very few longer than it takes the predictions to get to steady state. Now this might mean well over the open loop settling time, but ironically it could mean the closed loop settling time. The input horizon should be long enough to capture the ideal closed loop input trajectory. Now, if you've got a very large weighting on the inputs, this could be close to the open loop settling time, but again, it might also be a lot quicker. Some caveats. So far, we've only considered the unconstrained case. The best horizons may well change in the presence of constraints, such as rate limits on the inputs, but the same philosophical thinking will apply, that you need to look at your sort of closed loop responses and say, well, how big do I need the input horizon to be? How big do I need the output horizon to be to deal with these types of scenarios? So far, we've also ignored the availability or not of advanced information on the target, and we will cover that in a separate chapter. It's also noted that if you have open-loop, unstable systems, while GPC does seem to work okay in many cases, it's not really that well defined, and so you should use it with extreme caution. So conclusions. The horizons ny and nu are not tuning parameters, okay, and they're not options. If you don't choose them correctly and systematically, then the optimization could be ill-posed in that optimizing J may not imply sensible or good overall trajectories. And the reason for that is because optimizing J tells you the best you can do with restricted degrees of freedom over a restricted horizon. And essentially what we've told you here is that those restrictions, if those restrictions are too tight, then you may end up with an optimization which is ill-posed. If you want to have confidence that your algorithm is doing what you want, then your horizons need to be long enough, and you may need to do some offline testing to work out what long enough actually is. And what I've done is I would recommend beginning from values that are close to the ideal closed-loop dynamics. And you might think that's a bit circular, but basically what it's saying is find the ideal closed-loop dynamics, and from that you will know what you need the output horizon to be and what you need the input horizon to be in order for GPC to be able to deliver predictions which match the dynamics you actually want. Now some remark. If you're happy with the open loop dynamics, and we have mentioned this before, and thus an input which essentially moves directly to the expected steady state, then there's a much simpler alternative. You can almost avoid predictive control altogether. You could do a GPC algorithm with NU1, NY very, very large, and lambda quite small, but that's quite tedious. You've got to do all the prediction matrices and the optimization, etc., etc. Alternatively, you could say, look, I know what the steady state value is, it's just given by this formula here. Why bother with prediction and optimization and all that palaver when I can just write the answer straight down? And if you do that, because the estimate for D essentially incorporates the feedback, you should get the same control law. And the key thing is now you don't need prediction and you don't need optimization.